So we tell sort of a half-truth in General Chemistry 1, where we learn solubility rules, characterizing things as soluble and insoluble. And the fact of the matter is, it's not that simple. Nothing is completely insoluble, and nothing is infinitely soluble. And there, of course, there's a complete range in between. And you know this, right? Imagine yourself taking something very soluble like sodium chloride and a half a liter of water, and you start spooning in a teaspoon of sodium chloride and it dissolves, and another teaspoon and it dissolves, and you keep going, putting in one more after another. And eventually, you know, probably from experience, there's a limit. It ceases to dissolve. And you might also imagine another experiment. What if you took a beaker full of dry sodium chloride and put 1 drop of water in it? Would that make a liquid solution? Of course not. Okay, so you know there's a limit there somewhere as to how much sodium chloride can be dissolved in an amount of water. And the same holds true for any other substance. It's also true, the other end of the spectrum, some things we call insoluble, but they're not really completely insoluble. Many people are familiar, for instance, take a piece of chalk, calcium carbonate, and toss it in water. You'll find that it does not dissolve. It just sits at the bottom of the beaker. You could wait a very long time and stir all you want, and pretty much nothing happens. Actually, in reality, it dissolves a little bit, and we'll be able to calculate how much in a little while. It's something like 7 times 10 to the minus 5 moles per liter of that chalk actually dissolved. It's just that you can't see that, okay? So nothing is completely insoluble, nothing is infinitely soluble, and there's a full range of possibilities in between. And we learn now that we have our ideas about equilibrium. We can calculate how much material dissolves and what's the maximum that can dissolve. And it's useful because you can tell then when will a precipitate form. But let's look at a first example. So let's consider silver sulfate. It's slightly soluble in water. So imagine, as depicted over here on the left, you take a beaker full of water and you put some silver sulfate in there and you dissolve as much as you can, and then the remaining silver sulfate, the excess that won't dissolve, is sitting at the bottom of the beaker. And you stir it and you wait and you stir some more, and no more will dissolve. That situation that you have there with some of the ions in solution, the silver and the sulfate ions in solution, and the solid at the bottom, those two are actually, it's not a static equilibrium, it's a dynamic equilibrium, and it is an equilibrium. Okay, some of the ions actually return to being solid. 2 silvers and a sulfate get together and make solid again, but meanwhile other silver sulfate is dissolving. So it's not a static situation, it's a dynamic equilibrium, and we can use our equilibrium ideas to figure out everything we want about it. So let's write down that equilibrium. Here it is. Silver sulfate solid in equilibrium with 2 silver ions and a sulfate ion in solution. We write an equilibrium constant for it. It has a special name. It's called KSP, for solubility product. And it's just like every other equilibrium constant. It's products over reactants raised to their respective powers of their coefficients. So you have silver squared times sulfate. But we leave out the pure solid, the silver sulfate, that you might think appears in the denominator because it's supposed to be products over reactants, but the reactant is just the pure solid, and we leave that out. So in these solubility products, what you have generally is just the ions on the right-hand side of the equation. each raised to their respective power of their coefficient. And in this case, silver sulfate, KSP at 25 degrees is equal to 1.2 times 10 to the minus 5. Where did we get that? From the back of the book. There's a table in your textbook. You can look them up online. You have to get it from somewhere. It's a known quantity. So that's the basis for calculating what the concentrations are going to be. But first, this solution that we have now, what we have depicted over here, it's a solution. You've dissolved as much as you can, and there's solid on the bottom in equilibrium with the ions in solution. That's called a saturated solution. Saturated meaning you've dissolved all you can. That solution is holding as many ions as it can. It's saturated, okay? And we want to study that equilibrium situation. We want to see what are the concentrations of the silver and the sulfate ions in that solution under those equilibrium conditions, the saturated situation. So, well, we can bring up an ice table, okay? The way you do these is under the solid, just don't write anything, okay? That doesn't figure in the equilibrium at all. For the initial line, nothing's dissolved yet. So say the concentration of silver and the concentration of sulfate are 0 initially. And then for every sulfate, you get 2 silvers, right? So one call X and silver we'll call 2X. And then as always, the equilibrium line is the sum of the previous 2 lines. You just have 2X and X. You put that into the equilibrium expression. KSP is 1.2 times 10 to the minus 5. That's the silver concentration squared times the sulfate concentration. Silver concentration is 2X, and then that also gets squared. And then it gets multiplied by X for the sulfate concentration. The fact that 2X gets squared, sometimes that bothers people a little bit. And to think about that, the concentration of silver is 2X. And then it also gets squared. Sometimes people think it's like you're using that 2 twice, okay? But this is the correct way to go about it. The concentration, we called sulfate X, so the concentration of silver is 2X, and then that has to get squared. And when you multiply that out, 2X squared is quantity 2X squared. 2X quantity squared is 4X squared, multiplied by X makes 4X cubed. You're going to see that pattern actually come up again. Anytime you have a solid like this that makes 2 of one kind of ion and 1 of another, you're going to wind up with that 4X cubed for these KSVs. But anyway, you go ahead and solve that, find X, and you find that it's 1.44 times 10 to the minus 2. Okay, so that's the concentration of sulfate at equilibrium, and the concentration of silver ion in solution is twice that. Okay, 2.88 times 10 to the minus 2. Okay, there's another term called molar solubility that we want to explain. It's simple, really. When someone asks for the molar solubility of silver sulfate, they're saying, how many moles of silver sulfate can I possibly get to dissolve in a liter of water? Molar solubility. How much can you get to dissolve in? How many moles can you get to dissolve in a liter? Well, every mole of silver sulfate that dissolves gives me 1 mole of sulfate in solution. So that concentration of sulfate, that number is the molar solubility. It's equal to that. Okay, so you can always do that. You look for one of the ions that has a coefficient of 1 in the chemical equation. That will be the molar solubility. Now, some of you will say, well, what if none of them have a 1? Well, you could take the one that has 2 and divide it by 2 also. Okay, but just think it's the number of moles that can possibly be made to dissolve in this saturated solution. And again, the only thing that changes the amount that the KSP changes only with temperature, okay? The things quoted in the back of the book and most of the time online, they're for 25 degrees, and most of your problems will be at 25 degrees. Sometimes, and you'll notice this in lab a lot, when you take organic lab and things like that, you heat things, you can get more to dissolve, okay? But these values are at 25 degrees, and the value of KSP would change if you raise the temperature. Let's do another example. This one's barium sulfate. A lot of people are familiar with that in lab. You make a precipitate and carefully weigh out how much precipitate you made, and so on. But let's calculate it just the same way as we did the silver sulfate a moment ago. Now the equation is barium sulfate just dissolves and makes barium and sulfate ions, and it's actually a simpler KSP expression, barium times sulfate, is 1.07 times 10 to the minus 10, so that's very small, okay? It's not a very soluble substance at all. It's noted for its lack of, its insolubility. Make an ice table, even simpler this time, right? First line, zeros, plus x, and the equilibrium situation is, they're both x. Put that into the equilibrium expression, and you have barium times sulfate is x squared. So all you have to do is take the square root, okay? So these the compounds that just split up into two, you get the KSP equals x squared. If you have a compound like lead chloride, PbCl2, that makes one of one kind of ion and two of another, you get the 4x cubed situation. And there are others, but those are the two most common. The molar solubility here would just be that same number, okay? So it's a bit of an easier problem. But actually now, the reason for doing this is not so much to calculate the maximum concentration in a saturated solution. The main thing about KSPs, we want to use them to decide whether or not precipitate will form. So that's a very helpful thing. So let's do an experiment or example like that. So precipitation, let's study the silver sulfate example. And here's a problem. Suppose we mix 100 milliliters of 0.213 molar silver nitrate with 150 milliliters of 0.250 molar sodium sulfate. The one solution has silver ions in solution, and the other solution has sulfate ions in solution, and when you mix the two, silver ions and sulfate ions could find each other, and if the concentrations are high enough, they may produce a precipitate, okay? We studied situations like this before when we were first studying equilibria. We defined a so-called reaction quotient, Q. So Q, the reaction quotient, looks just like the equilibrium constant expression, but you could put into it non-equilibrium concentrations and calculate it for the purpose of comparing it to K. So here, when we mix these two solutions, we're just initially, right after mixing, before anything happens, we'll calculate the concentrations of silver and sulfate and calculate. Now that isn't equilibrium yet, or it isn't, might not be, and we calculate Q. If Q is greater than K, then that means that you have too much product and the reaction is going to shift to the left in order to get to equilibrium. If Q is less than K, then you have not enough product and the reaction will shift to the right. We had these rules that we studied at the time, okay? So it's a fairly simple matter of trying to calculate out these concentrations, put them in Q, and if Q is greater than K, we'll get, in this case, a precipitate, because if the reaction moves to the left, that means ions are getting together and forming solid, and that's precipitation, okay? So we need to first find out how many moles of silver we have in the one solution, how many moles of sulfate we have in the other. We need to take into account that the new solution is going to have 250 milliliters volume because we mixed 100 with 150, and calculate these new concentrations. So let's do that. Moles of silver, all the silver is in the first solution. So 100 milliliters times 0.213 moles per liter, 0.0213 moles of silver ion. Moles of sulfate, 0.150 liters. And the concentration is 0.250, you get 0.0375 moles of sulfate. And the volume of the solution is now 250, so we can calculate the concentrations. Concentration of silver, 0.0213 moles in 0.25 liters, 0.0852 moles per liter of silver. Sulfate, 0.0375 moles in 250 milliliters, you get 0.150 moles per liter of sulfate. We simply put that into our expression for Q, square the silver, multiply by the sulfate, you get 1.089 times 10 to the minus 3. So that is significantly, almost 100 times larger than KSP. So that means we are going to get a precipitate. This reaction is going to shift to the left because Q is greater than K, and you get a precipitate. So that's really that's really what this process is. In a given situation, you have to figure out your concentrations, put them into an expression that looks just like the equilibrium expression. If it turns out to be greater than KSP, you get a precipitate. If less than KSP, you don't. So they're pretty straightforward problems, I think, and we'll try to get some practice doing those going forward. The only thing to follow this up with then is common ion effect. We'll study a little bit what happens if you try to dissolve a substance in a solution that already has one of its ions in it, and of course it suppresses the solubility a little bit. So we'll study that maybe in a subsequent video.